So today for this session, we have Dr. Praful Pai. Praful Pai is with the academic engineering team at MathWorks India, where he primarily works with academia in India towards making STEM education engaging and accelerating research using MATLAB and Simulink. He completed his undergraduate studies in biomedical engineering from Manipal Institute of Technology and his MS and PhD from Department of Electronics and Electrical Communication Engineering at Indian Institute of Technology, Kharagpur, focusing on non-invasive blood glucose monitoring using photo. Here he worked on developing an MRI brain template for the Indian population. He is passionate about learning, teaching, and research in multidisciplinary domains involving instrumentation, signal and image processing, statics and optimization, and machine learning. The topic of today's presentation is applying deep learning to medical imaging and signals. Now I invite Dr. Praful Pai to start the presentation.
Thanks, Tripti. Thank you for the invitation to present at NIT Silchar. So it's a great privilege to be joining everyone. So let me just start the presentation. Just give me an entire moment. Yeah, I hope the screen is up for everyone. Yeah, I'll go ahead and also remove the video. Yeah, so
Yeah.
sure. So good morning to all the entire audience joining us over the live stream. Today's webinar, the presentation is going to be on applying deep learning to medical images and signals. Before we begin, as we said, I'm with the education team at MathWorks, and I'd like to take a moment to kind of acknowledge that whatever I'm going to present today is not just my effort. It's something that several of the math workers have also been involved in. So moving on, let's just get like a few things going. So in case you have any questions, like please enter them onto the live stream chat, and we'll probably, if we have time at the end of the presentation, we'll take that then. And if you want any information on accessing MATLAB and Simulink, we'll cover that at the end of the presentation. And in case we aren't able to address any questions, and so you can definitely email me later on. Yeah. So this is a brief agenda that we'll be covering today. We'll first look at some introduction to deep learning and deep learning terminology. We'll look at deep learning for images and focus on what we can do using convolutional neural networks, and look at a transfer learning exercise for MRI images. So if you are not familiar with any of these terms, don't worry, we'll start from the very basic, and we'll give you a brief overview of each of these things. Then we'll move on to deep learning for signals, and we'll look at LSTM networks and look at a classification exercise for ECG signals. And we'll talk briefly about deployment of deep learning networks and inference at the very end. Yep. So to begin with, deep learning is the key technology driving the current AI megatrend. Yeah. The origins of artificial intelligence date back to the dawn of computing itself, right back to the 1950s when the first computers were born. The Turing test was put forth by Alan Turing and so on. That evolved to machine learning, like with around the 1980s, which primarily involves statistical methods that enabled machines to learn tasks from data without explicit programming. And finally, deep learning, which is a subset of machine learning, came forward in in the 2010s, like in the last decade, really, where neural networks with very lot of layers are used to represent learn representations that directly from the data itself. So although neural networks had been around since the 1980s, but they weren't really uh, used as widely as they are today. So we'll see why as well briefly. So as I said, deep learning is a subset of machine learning with automatic feature extraction. So deep learning learns the features and tasks directly from the data. So in comparison to machine learning algorithms, wherein you have to extract features from your input data and then apply your machine learning algorithms on this feature set, deep learning is essentially end-to-end learning, wherein you just supply your input data and say your target, and uh, the deep learning network itself does the feature extraction as well as classification or any regression or any task that you want it to do. So it's been in the news, or it's been popularized because its accuracy can surpass traditional machine learning algorithms, and it also skips the feature extraction step, which can be subjective at times. We may not really end up with features which are useful at all. Yeah. However, it is still good to contrast machine learning and deep learning for a bit. So as I said, if you say your task was identifying a car from image, yeah. So what you would do in traditional machine learning is you would look at extracting a bunch of features from it, give it to the machine learning algorithm, and look at finding a classification, right? So here in the feature extraction step, we specify the nature of the features that we want to extract, the type of model that we want to build. So where is it a linear boundary? Is it a non-linear boundary between two different classes? Whereas in deep learning, as I said, it's end-to-end learning, which learns the features itself right from the images. Okay. And what we need to specify here is only the architecture of the model. We don't really need to specify any specific sort of feature set and so on. Right? The architecture of the model itself defines what sort of features are extracted and how it is classified. Right? And when should we go for machine learning versus deep learning approaches? So a good guide would be these two questions: whether you have good hardware and whether you have lots of data. So if the answer to both of these questions is yes, then you go for deep learning for your problem. In case the answer to one of these questions or both of them is no, I would say that it's better if you stick to with machine learning algorithms for your data set. All right. So, how essentially does deep learning work? So, deep learning uses neural networks and works similar to how we as humans learn. So, uh, if it's just a bunch of nodes interconnected to each other, and uh, each of these have just multiplication and addition blocks essentially, which operate on some numeric data. Most commonly, deep learning can be used for classification, wherein the output is categorical. You're like the object classification problem that we just saw in terms of differentiating a car from the pictures. Or deep learning can be used for regression, wherein the output is numerical or continuous in nature, and takes on the form of say something like predicting the value of how much energy is going to be spent in the coming days or weeks from the grid. So I hope this gives you a good idea of like what deep learning can be used for. Yeah. So, so what does a deep neural network um, consist of? So, deep neural networks basically consist of individual neurons arranged in layers. And as I said, each neuron has some multiplication factor, which is called a weight, and additive uh, term called bias. And it takes in numeric values. There are a bunch of neurons arranged in layers, and there is an input layer which takes in the numeric inputs, and there's an output layer which corresponds to the classifications that are there. And there are a bunch of hidden layers in between. Yeah. And there are different layer combinations which are involved in different neural networks and different neural network configurations. And what you can change in each of these nodes is the weight and the bias. So the node as well as the connections between them. Uh, uh, so the learnable weights and biases are present in between these, and these essentially mm, learn a representation of of the task that you want to complete. So if your task is say detecting tumor in an image, so the deep neural network is essentially uh, trying to learn that representation through a combination of features, through a combination of weights and biases, which gives you the desired outcome. So in deep neural networks, so information, as in the input data that you are trying to kind of use, is passed forward in a forward pass. So information is fed into the input layer, and you get a particular output, while the weights and biases are adjusted in a backward pass using something known as backpropagation. And this essentially is like a gradient descent problem, wherein you are trying to reduce the error or misclassification uh, by uh, modifying your weights and biases such that this increases. Right. So why did deep learning, suddenly become popular? So that was because deep learning models could match and surpass human accuracy in a lot of problems. So this graph is from the uh, ImageNet Large Scale Visual Recognition Challenge, ILSVRC, which is essentially an image recognition challenge which had been going on. So till 2011, primarily machine learning algorithms were uh, winning the challenge. So the machine learning so the challenge essentially is to kind of identify what a particular image is and what it corresponds to and give out a label. So so till 2011, machine learning models, were topping the challenge with, as you can see, accuracy rates of somewhere around 20 to 25%. Right. What happened in 2012 was a deep neural network uh, actually came in and cut the error rate in by 10%. So you get like error rate of 15% in 2012. And in 2015, actually a strange thing happened. So the neural network which won the challenge in 2015 actually surpassed the error rate or human accuracy that uh, that was there. So this essentially means that if a bunch of humans were to sit and label these same images from like select label for each of the images that is shown to them, then they would label 7.5% of them incorrectly. However, the machine learning or the deep learning algorithm does not. So its accuracy is far greater. Right. Um, so there are also a bunch of enablers for deep learning, which kind of helped in it succeeding. Yeah. So even though neural networks were around since the 1980s, deep learning just came about in the last decade because of large publicly available data sets, like the one used in the ILSVRC challenge. Also increased GPU acceleration from a ton of hardware which became available around this time also was helpful, as well as a bunch of world-class models like the ones which uh, won the ImageNet challenge. So researchers put such neural networks or pre-trained neural networks, as we call them, out into the public domain. And as you can see, so even though researchers were working on a different problem, people could use these pre-trained networks and modify them for their own tasks. We'll see how we can do that in the later part of the presentation. So deep learning applications in medicine. So there can be a ton of applications across. So if you just see at these 4 applications which were done using MATLAB, uh, so uh, so there is, if you see at the first application on the right, so the University or Hospital Heidelberg, so they essentially looked at semantic segmentation of histopathological images. So these are optical images of the slide, and the objective is to essentially segment parts of the image into different, sort of tissues which are outlined there. Right? Genentech, which is a commercial firm, also had something similar, wherein they use CNNs for digital pathology analysis of tumor images. This particular user story on the bottom from Ritsumeikan University. So this was where the researchers used deep learning for generating high resolution CT scans from ultra low dose CT. So CT, as you may know, uses X-ray images to reconstruct the image. Use X-rays to reconstruct the image, and to get like a very high quality image, you may need to expose the patient to X-rays which is not recommended, like which is not suitable. So what they did was they trained a deep neural network to kind of reconstruct the image from low dose X-rays, and they could still get good image quality. Right. And finally, this final user story from University of Texas at Austin, wherein deep neural networks were essentially used for converting your brain waves to words. So this like sounds very science fiction like. So here the researchers took in MEG data, so magnetoencephalographic data, which is similar to EEG, basically a representation of the electrical activity in the brain, and use deep neural networks to finally decode speech, as in to decode that what was the person trying to say or utter when thinking this. Right. So I have inserted a link to all of these in the slide, and we'll be sharing these slides as well as any code that we'll be covering here with you. Yeah. So as I said, MATLAB was used in all those 4 user stories that I had shown earlier, and the deep learning workflows in MATLAB work across different domains, right? From computer vision and image processing problems to if you have control design problems or data analytics problems, and like autonomous driving or any sort of essentially any sort of problems that you can think of in the engineering and scientific domain. Say it might be genomic data analysis, so you can still do that using MATLAB. And it I would like to highlight here that it's designed specifically for engineers and scientists to solve these same problems, and so with minimum coding effort, you can kind of look at prototyping and deploying your prototyping and testing, and deploying your problem. Yeah. So let's look at a small example for deep learning now. So yeah, this deep learning in pipelines. So as I said, deep learning involves neural networks, deep neural networks. So we'll load a neural network called AlexNet here. So this is a pre-trained neural network which I was talking about. So you can do that in MATLAB by simply typing in net is equal to AlexNet. Yeah. You can take in any particular image which you have say I downloaded an image off of the net and you read it into a variable. So you use it, you do that using the imread function. So following that, there is imshow. We'll just see what the image looks like, and we resize the image to fit the network. So AlexNet is a network which has a fixed topology, right? So which has a fixed number of input nodes, a fixed number of layers, and so on. So if you so essentially whatever data that you have to feed into the network, you have to like modify it to fit the network itself. So that's what we're doing here with the im resize function. We're resizing the image to a 227 cross 227 size, and we'll see briefly why. And finally, classify. So you use the function classify, just enter the neural network that you have along with the image, the resized image that you have, and you'll get an answer right away. So essentially you just used 5 lines of code, imported a network, read in the image, and resized it and classified it. All right. So let me just demonstrate the same thing to you over in MATLAB. Yeah. So yeah. So this is the MATLAB interface that you get. And what I'll do is I'll do this entire thing here itself. And let me just download an image off of the internet for that. So say, yep. So this is a different image. So let me just, save the image here. I'll just name it test image. Okay. So the first function was net is equal to, hope this is visible. Yeah. So the first function was net is equal to AlexNet. Yep. So when you do that, you get like a variable called net with a series, which is a series network with a bunch of properties in it, right? So as you can see, this says layers 25 cross 1 and then neural net CNN layer, right? So if you just click on this variable in the workspace, you'll get to see that what exactly that corresponds to. So you have a bunch of layers, your input names and output names. If I see the bunch of layers, yeah, so there is an image input layer, a convolutional layer, something called a ReLU layer, cross-channel normalization, max pooling, and so on and so forth. And if I click further on each of these, you'll get like information on what it corresponds to, or further information on each of these layers. So if you see, I clicked on the first layer and you saw the input size over here was 227 cross 227 cross 3. So so we'll go over so that's why this neural network topology is fixed over here. So that's why you kind of resize the image. Yeah. So let's just close this for now. Let's just read in the image. So imread. I'll just take in test image.jpg. I'll suppress the output. So as you can see, this is a 720 cross 1280 cross 3 image. What I'll do is I'll resize this. So I is equal to, I'll resize, and I'll resize it to 227 cross 227. So now you see that the variable size has changed to 227 cross 227, and I'll go ahead and classify it. So classify net, I. So as you can see, it gave me this particular categorical output. Yep. So here I just wanted to open up an app which helped you do the same thing. So if you go into the apps tab on MATLAB over here and you open up these bunch of apps, you'll see a bunch of apps under machine learning and deep learning. So these are basically GUI front ends to what I just did with code. So if I click on the Deep Network Designer app over here, yeah, so it will help you design, visualize, and train deep neural networks. So let me just open up the Deep Network Designer here. So I've just opened it up previously. So this will open up this app. And you can see you can create networks from scratch. You can create networks, import networks from Workspace. And then you also have a bunch of pre-trained networks like AlexNet here, which you can kind of add in. Yeah. So I wanted to kind of take on AlexNet, right? So I can just click on this AlexNet. And you can see that this will open up AlexNet with these bunch of layers. So if you just see, I can zoom into each of these layers. So there is an input layer, and you have all of these information here, and then a bunch of layers, which and finally ends up with an output layer here. So you can add on new layers right from here just by dragging and dropping, and then you can kind of modify these networks over here as well. You can simply drag, drop, and so on, right? So this can kind of, there are a whole bunch of layers available here, and we'll see something on what each layer does. Not for the entire, not for the entire list, but for something to give you an idea of, what each of these layers are all about. Uh, you know, but just to give you an idea, so you can design your network over here, select your training data, select your data in which you have to do your work, as well as do your training and everything over here. Yeah. So you can also finally kind of choose to export the entire thing and generate code out of it. So if you are kind of you don't really need to do open a GUI every time you need to do this. So you can simply generate code after the first time after doing this, and then work with that. Yeah. You can auto arrange networks and also analyze networks early on. So while designing the network, you don't want to kind of design a network and use it for training and then realize there was an error in the design phase itself. So what the analyze network function does is it will help you kind of analyze a lot of whether your network is designed well, like as in there is no mismatch between uh, uh, there is no mismatch between like uh, between your one layer and another. So yeah. So let me just get back to the presentation now. So you could do that. So now if you could do the deep learning on images, so deep learning on video is essentially processing images from that video, like the or individual frames from that video. Yep. So what we are essentially doing there is again loading the neural network, say something like using a camera or a video file as input, and then running a loop wherein we're taking snapshots from the camera, resizing it to fit the network, and then classifying it using that and fitting it to label, and we're just displaying the image. Yeah. So if we just see the video over here, so so this is taking in inputs from the camera, uh, and if I just hold it here, yeah. So I'll just pause the video. So you can see there are multiple objects present in the image. So however, the image is particularly focused around the backpack, and so the neural network again outputs 5 different words over here, and you can see a number across this. So what these words are the highest the classes with the highest probabilities. So even though this is 0.00, so if we kind of see the entire number, it would be very, there will be some fraction over here, right? And the backpack was the one with the highest probability. So the neural network said that this is the layer which can have the higher. This is the category which has the highest probability. So we can select it over here. Yeah. So you can see mouse, laptop. Yep. So as you can see, there are like multiple classes also over here. So there is a class for sunglass and there is a class for sunglasses. Yeah. So so it's not really. So when the previous network, which classified it as tiger, was what it was doing was it was just outputting the class with the highest probability, and we didn't see all of these. But you can access all of these by also looking at the neural network output just before the final layer, right? Let's move on. So as I mentioned before, like you can do a bunch of deep learning in MATLAB, and what MATLAB essentially enables is you to do the entire end-to-end workflow in deep learning. So what I mean by end-to-end workflow is like if you're taking on any deep learning or task, you essentially have four steps in that. Right? You can break your task down or project down into four steps. Your first step is accessing and exploring data, which can be from files, a bunch of databases, or a bunch of hardware sensors. You have to label and pre-process that data. So you have to say what category does this input belong to, and so on. You have to do some sort of data augmentation or transformation in case you have a smaller data set to work with. You have to pre-process it to remove noise and so on and so forth. And you also need to import. You also do your reference models, like if have other researchers worked on similar problems before. So how we imported AlexNet, you do that over here. Um, the next step is developing your predictive model, as in you're tuning your model to suit your task better. You're doing hardware accelerated training, and you're visualizing what the network sees. So essentially, you're doing your entire machine learning, or uh, you're tuning the deep neural network over here. And finally, once you are satisfied with the results, you are deploying it, or you're integrating your machine learning or deep learning model with systems. So you can deploy it as desktop applications, which run independent of MATLAB. You can deploy it onto enterprise scale systems on the cloud, or you can deploy it to embedded devices and hardware like NVIDIA Jetson board with a GPU, or a Raspberry Pi, or even something like autonomous driving system. Right? So let's look at the first two steps on here. That is the access and the labeling step. So deep neural networks, as I said before, takes in numeric data. So if the data is an image, so that essentially is a numeric matrix, right? So if it's a 2D image, it's a 2D matrix. If it's a 3D image, it's a 3D matrix. Or and there can be 4D matrices as well, like with different types of images. Right? If you have signals, these are taken in as numeric vectors over here. Um, and if you have, you can also work with text, which is again processed as numeric vectors or sequences. Yeah. There is a link to documentation provided here, so you can definitely read more if you are interested. So let's look at a couple of challenges in the data access and pre-processing stage. Yeah. So how do you access like a large amount of data, which is essential to deep learning, and and it might not really fit in your memory? So how can we do that? you know so these steps, what we found was the data access and pre-processing steps were the ones which we do not really think of during research, because what happens when we are doing your research and when you're doing your projects is we focus in academia a lot on developing our models. So as you can see, like a big part of research in academia is focused on development of new models and algorithms, while a tiny portion is devoted to developing data sets. Whereas it's the complete reversal of this situation in industry. What happens in industry is, uh, we devote a large part of our time on developing data sets itself, uh, just to cover all cases, and a smaller amount of time is devoted to developing models and algorithms. So these stats were really taken from Andrej Karpathy slides at Train AI. So uh, he's a director of autonomous driving at Tesla, and earlier he was a PhD student at Stanford. So he was just contrasting what he spent his time doing as a PhD student in comparison to what he does now. So uh, so this provides you an insight into how you might want to kind of uh, model your deep neural network projects as well. So a good way would be to balance both these things, right? And the message here is like MATLAB and Simulink can help uh, in accelerating your model development, as well as accelerating your data pre-processing and labeling tasks. Right. So let's address these three challenges here first. So how do I access data which might not fit in memory? And what if you have like an imbalanced data set, which has too many examples for one class and not enough examples for the other? And finally, how do I label my data faster? Right? So how can I access and load large amounts of data? So you use something called data stores. So instead of reading in each image like I did earlier using IMRead, what you use is a image data store, which reads in a bunch of images automatically, and however it reads them into memory only when needed. Yeah, you don't need to load all of your images or signal data into memory in one go, and do it only when required. So it's available for audio data stores as well, right? Finally, you also have tall arrays. If you're working with any big data applications, so instead of and if you're working with out of numeric arrays which are giving you say out of memory errors, so you can also use something called tall arrays, which are a very easy modification for you to make. So you can definitely read up more on this in the documentation, and also look through some of the examples which are there. Then how do I label my data? You can do that using a bunch of labeling apps which are present. So there is the image labeler and the video labeler, which helps you label images and videos. Then there is the ground truth and labeler, which is essentially labeling for autonomous driving. And for signal data, there is the audio labeler and the signal labeler. So there is so one is for speech and the other one for signals. We also have a big image labeler which is present on the file exchange. So if you have like huge images such as satellite images or something like optical microscopy images which can run into gigabytes, so then you can use this as well. So let's just look through a bunch of videos which show you how the labeling works. So you can simply read in images. Open this, and you can draw your bounding boxes in. So, and you can automate this entire thing as well, wherein you are trying to kind of choose your vehicle detection algorithms and so on. You can write your own algorithms for automating your labeling tasks as well. Right. So that was image and video labeler. So how can you label signals? So you take in signals, you can kind of modify this and so on. And finally, you have the big image labeler, which I talked about. So this is on the MATLAB Central page. So let me just open up MATLAB and quickly show you where you can find these. So again, you can go to the apps tab over here and just click on the drop-down menu and type in label. So you can see that, so all of these 5 labeling apps appear. So there is the image and video labeler in the image processing and computer vision section, the audio and signal labeler in the signal processing and communication section, and finally, automotive section has the ground truth labeler for your autonomous driving applications. All right. So what if there isn't enough data that I can work with, and or what if there is a data imbalance? So in that case, essentially say, and this happens a lot in the medical domain. So essentially, the abnormal case data that we have is a lot less in comparison to the normal cases that we have. Right. So what may happen if you train a deep neural network with an imbalanced data set like this is it might just not work well enough, or it might give you it might favor the class which it sees more or which it was trained on more. So the class essentially with the maximum number of examples in the input data set goes on to become the more favored class, right? So how can you address that? So you can do that using data augmentation. That is, you transform your data, or you can generate new data called using something called generative adversarial networks, or GANs. Uh, and you can also synthesize new data, or you can model your system and synthesize data for a bunch of operations. You can copy the data over and so on, right? So we'll maybe look at an example of this in the demonstration that we have later on, right? But for now, let's move ahead. Yeah, excuse me. Yeah. So we covered the data access and pre-processing steps. So next, let's select a network architecture. So what sort of architecture do we select? So as I said before, so if you have images, then you select something called a CNN, or a convolutional neural network. So this is a deep neural network, a special type of deep neural network. Whereas if you have signal or text data, you'll see ahead that we can use either CNNs itself, or we can use a different type of network called LSTN, or long short-term memory networks. Yeah. We'll cover both of them in a bit of detail. Yeah. So here, let's focus on images first and talk about CNNs a bit, and then look at where we can go. So if you look at deep learning for images, so there are essentially 4 tasks which we can do. One is object recognition, wherein we are taking in inputs as images and then uh, what putting out a class. So essentially, what we did with the Richard Parker image or the test image earlier. We can have object detection problems, wherein you're detecting what part of the image has a particular object in it, like, for example, the sailboat, building, aeroplane in the image is marked with bounding boxes. You can do image to image regression problems, wherein you're starting from, so something like super resolution. So if you know what it is, wherein you're trying to increase the resolution of an image. So you're going from a low quality image to a higher quality image, as you can see here. Uh, you can do that, or you can do semantic segmentation, as in you can, instead of labeling the entire image, you can provide labels to each and every pixel in the image. So for example, in this image here, you are labeling different parts of the road as green, different vehicles coming over here as blue, or you have your brain tumor segmentation over here, wherein uh, you have some part of the brain marked as normal, whereas the tumor is marked in a different color, and so on. Right. So these 4 things are essentially what your majority of deep learning problems in with images can be classified into. And any other tasks may involve, like, combining these things together as well. So let's look at convolutional neural networks, which are typically the neural networks used for these deep learning with images here. So CNNs, or convolutional networks, as they're called, are a special type of network which can be used for classification, regression, or feature extraction. Right? So, as I said, it consists of a bunch of layers, and it essentially looks at finding out local features and then uses those local features to do a classification. Right? Let's look at how a pixel or a numeric value coming at an input travels through a CNN. Right? So if you have an input coming over here, so initially there are a bunch of networks, a bunch of layers which are used essentially for feature learning, and then a bunch of layers which do your classification. You know, so you have in the feature learning phase, you have convolutional and ReLU layers along with pooling layers. So you have these three layers: convolution, ReLU, and pooling layers, repeated again and again to get more and more localized features. So these essentially learn things from the images. And finally, in the classification layer, you have your fully connected layers and softmax layers, which we'll see what they do shortly. And finally, it gives you the categorized output, right? So each of these layers has some weight and bias, and if you look at a simple network like AlexNet, the number of weights and biases or the number of parameters in the network comes out to over millions of parameters, or nearly 60 to 62 million parameters in the entire network. So modifying each of modifying, like, one thing may involve modifying 60 million values. So that is why we need a large amount of computational power as well as a large amount of data to train these networks. So what do CNNs do? So CNNs essentially look for patterns in the network, right, and identifies the most common pattern or recurring pattern within the training data, right? So like if you see this particular image of like a O-shaped over here, and then you see these three masks or filters. So if you've done any sort of image processing earlier, so you'll see that so these two masks on the left and right uh, appear in this image. So this one is present here, while this one is present over here, right? However, this mask in the middle does not appear, right? So what the CNNs do is it will train over a bunch of images and come up with a bunch of filters which are common across all the images in the training data set, right? So if you look at what it does is it is essentially moving these random filters over the entire image like you would do, and it is computing where it finds a match, and if it finds a match, then this gets stronger and stronger. Yeah. So as I said, just looking at the number zero, so all of these filters would be common in here, right? Yeah. So all the patterns are compared to the patterns on a new image. So once you have come up with a bunch of filters, so this is again a zero written in a different form, right? So the patterns that you saw in the last slide, so you'll also kind of try to see these things in this particular presentation as well. So we'll this particular image as well, and you'll see how patterns can start at you'll essentially move this filter from the left corner to through the entire image and repeat it, right? So I hope this gives you a fair idea of what CNNs do. And so good pattern matching in convolution basically improves the chances that the object will be classified properly. Yeah. For example, this image will not match well against any of the patterns for the number zero. So this is not classified as a zero. All right. So this will do only very well against this particular pattern and not any of these patterns. So hence, this will not be classified as zero. Yeah. So I hope this gives you a fair idea of what is going on inside of a CNN. Okay. So then comes individual layers like the ReLU layer. So ReLU stands for rectified linear union. So this essentially consists of a rectifier or an activation function. So as rectifiers go, you are essentially making any negative numbers zero, and you're retaining the positive numbers. So if you have like an input like this matrix uh, to the ReLU layer, what the ReLU layer will do is whatever negative numbers are present in the input, it will make them zero while retaining the positive numbers. Like this introduces a bit of nonlinearity in the system as well, and helps the neural network learn. Then there is the pooling layer over here. So what pooling does is essentially it's a downsampling operation, and it downsamples the image while preserving important information. So uh, it is mostly done using max pooling. So what that essentially means is, so if you have an input like this 4x4 array, so what max pooling does is it will decide a stride length, so to speak. So that this 2x2 is something called as a stride, and it will take in these sized smaller chunks, and it will in max pooling it will take the maximum of these inputs and give that at the output. So if it does that on all four, so you can see that the maximum of all these four was 4, that came out here. The maximum of these was 8, that was here, and so on and so forth. Right. So yeah, so you use 2x2 filters with a stride length of 2. That is essentially you move 2 steps ahead. You can also choose to move 1 step. So in that case, your image will be like from a 4x4, you'll be moving down to 3x3, and so on. So average pooling and min pooling exists too, but max pooling is the one which is most commonly used. So finally, what are the last layers in the network? So classification problems end with usually 3 layers. There is a fully connected layer, which basically looks at higher level features corresponding to a category. Uh, so as the name suggests, it is fully connected with each of the layer inputs. And it essentially computes the score for each category. So the percentage values that you had seen into one-dimensional vector, which corresponds, whose size corresponds to the number of classes that you have. So the softmax layers will turn these scores into probabilities, and finally the classification layer will categorize the image into one of the classes. That is, it will essentially select the one with the highest probability as the class. Right. In terms of regression problems, they end with essentially 2 layers. So there is the fully connected layer, and the regression layer. So we'll not be covering regression say if you're trying to predict the rotational value of trying to correct for that. So you can do that using a regression neural network, and then correct, apply the reverse correction to have them standing upright. All right. So if we just look at the deep network designer, all of those things appear over here. So there is like a convolutional layer. There is there are pooling layers over here, and you have object detection layers and your output layers over here. So you have a classification layer as well as you have your regression layers. All right. The softmax layers are also present over here. Okay. So let's move ahead. So feature maps are essentially outputs of the convolutional layers, and say neural networks which are trained on a particular set of images, like AlexNet was trained on millions of images of millions of natural images. Then you can use AlexNet and the features that the CNN like AlexNet learned for your other object classification problems or object recognition problems. Right? There are a bunch of examples which you can look through for details on this. Right? Now that we've covered like CNNs in quite a bit, mm, like we so here I think it would be good to clear out uh, what parameters and hyperparameters are. So parameters are things which are chosen by the network. So these are essentially numeric values which are calculated within the neurons, and these are the learnable parameters are something called like the weights and biases in the neural network, and which are adjusted during the training. Uh, by comparing the final output that the neural network gives out with to what the target or the desired output was. While hyperparameters are things that we set manually. Something like the stride length or the number of hidden layers, the learning rate, mini batch size, and so on. So these are some things which are uh, set by the user, and these are not really changed during training. So changing hyperparameters is done during network tuning. So essentially, you're trying to find out what is the best learning rate which can work. So you can do that. However, that would be an entirely new training run and uh, not a single uh, not a which is entirely independent of previous training runs. All right. Uh, so if you're doing any sort of hyperparameter tuning, so you can look at a particular app in MATLAB called Experiment Manager. So if you go into the machine learning and deep learning section, there is the Experiment Manager app, which can help you design and run deep learning experiments and compare deep learning networks. So if you're doing any sort of hyperparameter tuning, so if you want to select uh, what is the best neural network from 5 different neural networks, then you can definitely use something like the experiment manager to kind of do that. Right. So how do I know which layers to use? So as I said, if you have to do feature extraction from images, you use 2D or 3D convolutional layers, and if you're doing the same with sequences or signal or text data, you use LSTM layers and so on. For activation functions, you have the ReLU layer or the hyperbolic tangent for doing the ReLU for doing the activation, and then you have normalization layers as well, such as dropout and batch normalization, which can come into play. So if you want to kind of read up more on what each of these layers does and what is essentially the function of each of these layers, then you can definitely go through documentation. There's a fair bit of documentation as well as additional links in the documentation which you can read for getting more details over here. Right? So uh, yeah. So essentially, there are two training approaches for deep learning, right? So either uh, you can train deep neural networks from scratch, or you can use pre-trained models over here. Right? So if you're training a deep neural network from scratch, uh, what you can do is you define each of these layers and then go ahead and train the entire thing. So if the weights are initialized to some random values, and then you have to adjust it for your task. Uh, so you do that, yes, but only when available pre-trained models do not work. So if available pre-trained models such as AlexNet and others provide a very low accuracy for with a car is classified as a laptop. So if you face something like this wherein you have very low accuracy on your data set and you have a bunch of different category definitions or a different task, so then you need to train your own models there. Also, pre-trained models may not be really be available for your data, because most pre-trained models or may be trained on natural images, like images of natural scenes which are occur in real life. Whereas you may want to kind of train your network on a different type of image, like say your CT or MRI or infrared image, or optical or an optical microscopy image, or a painting. Yeah. So in that case you will have to kind of uh, retrain uh, some of the neural networks that you use. So you may need to you may need to modify your pre-trained models. You can use them, but you may need to modify them, and you yeah, may not want to develop one from scratch, but you cannot use the pre-trained models right away as such as well. Right. Also, training deep neural networks from scratch is difficult, because it will take a bunch of your time, and it will not really kind of it will take hours and hours to do that. All right. So let me take a moment here and just go over some of the questions which are there. Yeah. So um, yeah. Let me. Okay. So yeah, I can see a bunch of questions which are similar to uh, like I can see a bunch of questions related to whether MATLAB is better or Python is better, and so on. So I think you can definitely use both. I would say if you're focusing on solving the engineering problem at hand, then MATLAB has a ton of things to help you do that, right from uh, your entire, importing your images, labeling them, processing them, tuning, and finally to deployment. Whereas it might be a little more difficult to kind of do your entire thing on Python, just because of the difficulty in setting up the environment. So that might be a challenge. So but then I work for MathWorks, so I please use whatever makes your deep learning work go better. And I'll also at the very end highlight how you can co-execute MATLAB and Python, so you can use both together as well. Right. I don't see any more major questions separately, so maybe we'll move on. Yeah. So as I said, there are two different training approaches for deep learning, right? One is from scratch, and the other is using a pre-trained model. So what what happens when training using a pre-trained model is you use a bunch of pre-trained models such as the ones mentioned here. So like AlexNet, BGG16, BG19, GooglyNet, and so on. So you have a bunch of all of these networks available in MATLAB, uh, and they have predefined layers and predefined parameter values, and they can be used directly for inference, for the task that they were designed for without training. So like how we used AlexNet in the first demo, you can use them directly without any training involved. Uh, and as I showed you in the Deep Network Designer app, a bunch of these are available over here. So you can install, AlexNet I already have. Other networks you can install, like the Exception Network or the Places 365, GooglyNet, and so on. Yep. So you can do that. Also, if you are working with, if you have come across like things that others put out, if you other researchers have put out networks designed in other frameworks like TensorFlow or PyTorch or so on, then you can import all of these into MATLAB. So MATLAB has a Keras and Cafe importer, using which you can directly import into MATLAB. Or for other networks like TensorFlow, Cafe, or PyTorch, you So you can import the network into Onyx, and then using the Onyx, you can import it into MATLAB. So if you are looking to do that, you can go through the documentation, and I think you'll find lots of help there to do this. Okay. So let's look at using how we can use a pre-trained model and how we can modify it to do what we want. So this thing is known as transfer learning, right? So what it does is it will basically load a pre-trained network. So as I said, there was a bunch of layers in the initial layers do the feature learning task, whereas the final layers do the actual classification task, right? So what we do is we replace the final layers. So we retain the feature learning, but change the final classes and use the new layers to learn feature specific tasks for your data, right? And we train this again on our data set. So instead of training on millions of images, we can train this on hundreds of images, or depending on how many number of classes that we have. And finally, use that use the final network that we are happy with for prediction or inference, right? So let's look at an example for classification of MRI images. The objective here is to take in a bunch of MRI images, take in the mid slice. So MRI images are three-dimensional in nature, but what we are doing is we are taking the middle slice of that MRI image, um, and we are using a deep neural network to say whether this MRI image was taken from people who were between or ages 3 to 5, ages 7 to 12, or adults. All right. So I hope this gives you an idea of what the problem is. So it's a 2D image classification problem. We're assigning 2D images. We're starting with 3D volumes, taking on 2D images, and then trying to classify it into one of these three classes. All right. So let's just go open MATLAB for a bit. Yeah. Yeah, so this is a live script. So these are essentially not just M files. These have your code. These have rich text, as well as hyperlinks, as well as links to other M files and within different parts of this particular M file itself. Um, so so we can run this, or we can insert equations, images, and so on right from here, the insert tab over here. So what we can do is we'll run this quickly bit by bit, and then go ahead and do the rest, right? So these images are taken from an open neuro data set. So either I can run each section in advance, or I can go ahead and you know click on this blue tab or at the on the side, on the left side here, and run it, and the output will show up on the right over. All right. So this has been around for quite a bit. I think it's been around for almost 5 years now. If you aren't using it, I highly recommend you use something like this instead of your regular .n files. You'll see the extension here is .mlx instead of .m. Yep. So let me just run this section and advance it. So here where we have your root folder. We are constructing the full file name, and we are using something called Nifty Read, which is a file format read for reading this data in. All right. So if I just this, yeah. So this reads in the data and gives me this image. As you can see, I can kind of visualize this 3D image over here, and it's essentially taking this slice that is shown over here. So yeah. Now let's go ahead and explore what sort of data set is there. All right. So as you can see, this is the sort of data which is there. So you have the images, you have the ages, the age group, and whether it's a child or adult. I have a gender, handedness, this and that, and a bunch of other parameters. So if I click on this, yeah, So the participant data has something like this. So there are 65 records corresponding to ages 3 to 5, 57 corresponding to ages 7 to 12, and only 33 of adults. Right. So you can do that by simply using this summary command, and you're just doing a bunch of indexing, array indexing over here to kind of get that data. Now, if you have to explore that mid-slice data, so we have a function which we have written to do that. This will kind of take in the middle slice from all of these 3D images, and so yeah. So if I click and do that, so yeah. So this are exemplar images from each of these classes. So age 3 to 5 middle slice, and age to 7 to 12, and an adult teen image. Yeah. Now let's prepare the data set for deep learning. So you have you have a bunch of options ticked here for applying skull stripping, that is removing the skull from the image, and these are essentially data pre-processing tasks that you can do. And finally, I want you to focus on here. The image data store. What it The image data store does is, you did not really see a image read command exactly. So image data store will read the entire set of images from this folder, and along with its labels, as well as the sort of file extensions that are there. So if I just run this, so now it is reading in these images here. Yep. So now it has ended up reading it, and the image data store is there. So now you are selecting images at random from the group, and like comparing how they appear side by side. So now if you see in the previous comparison, so there the skull was visible. Now in this particular comparison, you can see that we have done some pre-processing. We have done the skull stripping, as we say in when dealing with brain MRI images, and the skull is no longer there. Yeah. Also, we have rotated these slightly to kind of point in the same direction, and so on and so on. All right. So how do we divide this into training and evaluation? So you use something called split each label. So you can use split each label, provide the image data store, and provide what percentage of data you want for training, validation, and testing, and so on, right? So you use the split each label to use 0.85% into training and testing images. Then the training data set, you divide it further. So 80% of that, of the training data store, you are dividing into training and validation. All right. So if you just look at this, then this is what it looks like. So we started with something like, this is our training set. 89 images from 3 to 5, 78 from 7 to 12, and 45 images of adults. And similarly here over here. All right. Yeah. Now we'll take a network called ResNet and use it for brain age classification. So so these are basically ResNet was trained on ImageNet again. ImageNet on the ImageNet database. So it has 18 layers and classifies objects into 1,000 categories. All right. So what we are doing here is like adjusting the image size to fit the ResNet network. All right. So, and finally, preparing this for transfer learning. So as you can see, we replaced the final layer of the ResNet network with, so earlier it was a fully connected network of 1,000 categories, but now we have replaced it with a new fully connected layer, as well as probabilistic layer and a classification layer. All right. So here, we can see just this graph over here, which shows us the same thing, which I just put out. So we put in a fully connected layer and display this. All right. Now let's just go ahead and apply image resizing and data augmentation. All right. So this will augment the amount of data that you have. So currently we have your training, validation, and testing data store. And so after augmentation, this is the sort of image counts that we have. Right. All right. Following that, let's set the training options. So you set the initial learning rate, your mini batch size, maximum epochs, and your validation frequency, and so on. And you just start the network. So all of these you put it into a one single variable called train ops, where you are setting the initial learning rate, your validation frequency, your mini batch size, and so on. And you're just also selecting like a bunch of other things, such as this kind of gradient descent method, the optimization method that you want to use, and so on, right? So you can simply click that, and yeah, and you can use you can open up the training over here, right? So now if I click on this, your training network simply takes on your data store and your network as well as your training options. So it just takes in these three inputs and gives you the output over here, right? So this is how the training progress looks like. So you have a graph for accuracy as well as loss, and it will start with a training iteration over here. All right. So as you can see, it's doing 60 iterations, which I set. You can see what epoch it is on, number of iterations per epoch, and the validation frequency. So every 4 iterations, it will be validated once. Yeah. So as you can see, it starts off with a network which has 20% accuracy and so on. So what I'll do is I'll let this training run, and let's get back to the presentation, and then see what comes of it. Yep. In the meantime, let's go for look at deep learning for signals. Yep. So in case of signals, what you can use deep learning for is for these 4 tasks. You can either detect single signal events. So when a particular word was spoken, or when arrhythmia was detected, or when in an ECG, or when a particular type of waveform was detected in, say, the EEG. You can segment the images into the signals into different tasks parts. For example, if you're looking at taking the PQRS, the ECG signal, and dividing it into PQRS and T waveforms, then you can do that using the deep neural network. You can classify signals into normal, abnormal, those categories, and so on. And finally, you can also process the signals to kind of remove noise, or say do some sort of source separation for this. All right. So again, as I said, for signal or text data, you can use CNNs or you can use LSTMs. Yep. So the way you use CNNs is essentially convert your 1D signal data into a 2-dimensional format by using taking a spectrogram, or so a time frequency representation of the signal, or a scaleogram, and then feed that 2-dimensional representation of that 1-dimensional signal into the CNN. Yeah. If you're using LSTMs, however, you can directly input the signal, as we'll see right now. Yeah. So you can use LSTM networks wherein you're feeding either your signals directly to your neural network, and you have like a bunch of layers over here, or you can also extract features and then feed that to the network. So we'll see briefly why that might be important when it comes to using signals with deep neural networks, why feature engineering might be important. Yep. Or as I said, if you're using CNNs, you can convert it to a 2D representation and then use the CNN. All right. We'll focus on the first bit for now. We've covered enough of CNN, so let's look at LSTMs. So LSTMs are a type of recurrent neural networks. RNNs are predominantly used with sequences or with variable length data, and they use hidden layers to process your future input. Hence they are recurrent, and they have some memory. So what it essentially means is it will, in addition to your taking your input data at a given point in time, it will also take in your past output to for your prediction. So I think if I just go on to the next graph, yeah, next. So if you see, you have a bunch of inputs coming in from x0 to xn, your samples, which come into the network. And for each input, you get a particular output that is there. So now this output is also used with the next time step. So when giving input x1 to the network and predicting output h1, the h0 is also used for your prediction. So that's where the recurrent part of the neural network comes in, and that's why it takes into account previous data when making new predictions. All right. So as you can see this, right? I hope this made it clear. However, they have limitations, right? So in case there are very long sequences, so RNNs can suffer from short-term memory. So how many of your inputs do you take in how many of your predicted outputs do you take in while predicting for future inputs, right? So this leads to a problem known as the vanishing or exploding gradient. And how we can overcome this is by essentially using LSTMs. So there are a bunch of things that we can do using ReLUs and by downscaling or setting thresholds, but we'll focus primarily on using LSTMs to overcome this particular problem. Right? What LSTMs do is, in addition to using previous past inputs, we also provide past states. So it has some amount of memory uh, there, which carries past states back to the neural network as well. So uh, it essentially carries some sort of memory throughout your classification process and captures long-term dependencies which are present in the problem. Yeah. So they can be used for regression and classification. So this provides an overview of how you can use it. I'll not cover this in detail just because we're short of time. And as I said, your network architecture consists of an input layer, LSTM layer, or a bi-LSTM layer. And for regression, you end with a fully connected layer and a regression layer. Or if you are doing some sort of classification, then you have your fully connected layer followed by a softmax and a classification. So all of these are available in the Deep Network Designer. So please go ahead and explore this further. So I wanted to show you an ECG signal classification problem. I don't know if we have time enough for that. Maybe let's just see what the progress is on here. Yeah, so it's currently completed 34 or 60 iterations for the MRI age classification problem. What I'll do is I'll go ahead and stop the training right now. So yeah, so it takes a bit of time to stop this. And once this is stopped, let's, yeah. So this stopped the network, and as you can see, we were at somewhere around 80 or almost 90% or 96% validation accuracy, right? So yeah, so this thing shows up over here, And like if I see here, if I go on to the next section and run it, yeah. So I have trained my network, and now if I use the trained MRI network, so I've trained my network, and the trained network is in MRI net. Now if I use the classify function like how I did in AlexNet, so I did for I give the trained network along with the test data set or the test data store here. So I can get accuracy over here. So I get 95% of the cases I predicted it right. I can compute the confusion matrix easily by using confusion chart. And finally, also this is a important feature which an advanced feature which you can use. You can visualize what features were used by the network for coming to its decision. So this is known as occlusion sensitivity. So you are like deep neural networks were largely regarded as a black box, and that is why many people hesitated using them for critical tasks, because they didn't know why a deep neural network was making the decisions that it was making. So what occlusion maps do is it uses a function called occlusion sensitivity over here, and it gives you a highlight of what part of the image was focused on when the deep neural network was making that decision. So as you can see in these images over here, if I just pop this out, uh, so you'll see that these things over here, like the red regions were the ones where the network primarily focused on. So for the ages 3 to 5, it focused on this region. So and for later ages, it focused on this. All right. So this is correct with what most neuroscientists will tell you. So what happens is the ventricles in a person's brain, so they change their size, and the area around the ventricle changes with time. So that is why like this area being focused on for your classification of your MRI slice into different ages is actually correct, right? And so you can validate that using this. All right. So if I just run this, you can also view occlusion sensitivity maps for two older classes, and you have a bunch of references over here which you can see. All right. Um, okay. Sure. So let's get back to the presentation and maybe quickly go over. So I don't think we have enough time to go over this example. So let me just go over deployment and then take any questions that you have. So um, yeah. So if you look at the deep learning workflow, so we looked at a bunch of access and exploratory steps, pre-processing steps. We looked at developing the predictive models for the MRI example, and finally we looked at and now we'll look at how we can integrate it with further systems. Like, so if you have come up with a bunch of deep learning models on your on MATLAB, so you can easily deploy it to enterprise systems or onto embedded platforms with CPUs, GPUs, FPGAs, PLCs, and so on. All right. So you can easily deploy your machine learning, deep learning algorithms and have them scale for your particular application. You can do embedded deployment from your MATLAB code to C, C++, or CUDA code automatically, and use it and deploy it onto your target hardware. And you can do this for your inference tasks. So either you can deploy to GPUs from NVIDIA, AMD, or Intel. You can deploy it to CPUs or either Intel CPUs or ARM processors. Or if you're doing a bunch of deep learning using FPGAs, wherein you want to generate HDL code for your FPGA, you can do that as well. All right. You can also deploy it to enterprise IT infrastructure. So a lot of industries, what they do is their enterprise IT infrastructure works on a very different platform. So they have a cloud database. They might have cloud storage and other containers in the cloud, which contain both their data as well as an interface for them to take future actions. So you use something called MATLAB production server to help MATLAB talk to your cloud infrastructure, and it can handle requests through that, and help you kind of deploy your deep learning machine learning into the cloud. So many industries which have yeah, their cloud infrastructure running on completely different platforms, you can use that with MATLAB, and they are actually using that across different domains such as energy production, financial data analysis, and so on. Right. So I hope this gives you an overview of all the 4 steps. So deep learning in MATLAB has been, available for long. So we supported neural networks right from the 1990s, and officially support for deep neural networks began in 2016. Unofficially, it began a little earlier than that, using something called MathConNet. If you used that before, in 2020, what we have focused on is there are a whole bunch of examples for you to kind of learn from, and for you to go over and start your deep neural network uh, journey, or your deep learning journey. And you have the experiment manager app, which I didn't show, but it's definitely an add-on to something to help you do your deep learning efficiently and in as minimal time as possible. Yeah. I also showed you a bunch of labeling apps we have developed over the years, and so if you are doing some sort of point cloud analysis for autonomous driving and so on and so forth, then I think the coming releases will be definitely of interest to you for in terms of both labeling as well as processing as well as machine learning or deep learning tasks for autonomous driving. Yep. If you want to learn further, I highly recommend you go over a deep learning on ramp, which is a 2-hour online tutorial available free of cost on the MathWorks website. I recommend that you do this using your official or institutional email ID, but it is open for you to do using your Gmail or Yahoo or any regular email domains as well. So there is again a deep learning training which is there, which is a 16-hour in-depth course which takes you through the entire gamut of the deep learning that is present for in the deep learning toolbox. And a bunch of resources are also available for teaching deep learning with MATLAB. So if you are looking for curriculum support, or if you're teaching deep learning, and if you want us to, if you're confused about how to get started, and if you need help with that, then do get in touch with us. So you can visit this link. Also, you can write to us for that. So do get in touch. This is my email ID, ppy@mathworks.com, and we can definitely help you like get started, or like or do your wherever you are in your deep learning journey. I think we can help you scale new heights using MATLAB and Simulink.
Yeah.
So
So thank you, Praful. So some queries from the participants. First
sure.
query is, most of the MATLAB command work on 2D images. How can we
Yeah.
use it for the 3D image?
Okay. Yeah, I didn't cover this in the presentation, but most of the image processing commands, if you see now, work on both 2D as well as 3D images. And we actually have a shipping example for processing 3D images. I wanted to show that today, but as it was short on time. So if you just look at, uh, yeah. So if you just look at this particular example, 3D brain tumor segmentation using deep learning. So you can simply see like how you can read complete volumes. So yeah. So again, image data store works on not just 2D images, but it will also work on your volumes. Uh, so this is a semantic segmentation problem which I wanted to take on, but yeah, maybe some other time. But you can definitely visit this. This is a shipping doc example which you can go over. Uh, so what you can do here is instead of you know extracting like what happens is you extract different, you define pixel labels as well as you do patch extractions instead of regular 2D images, how you process them using deep neural networks. So uh, so you can definitely use 3D images with UNet, and I think if going over this example would help do that. Yeah. Any other queries?
The question is, if we use CPNN instead of CNN, will it be faster or any other solution?
So what is CPNN? Like
I
I'm
also
not sure what CPNN is. Uh,
okay.
yeah.
And other question is, for a 3D volume MRI scan, does data augmentation work or we have to convert it into 2D image?
Yeah. So 3D images itself. So data augmentation will work there as well. As was saying, yeah. So the data augmentation will work here. So if you just see this random patch extraction data store, so you can in 3D images, data augmentation works in the form of taking smaller chunks of that 3D image. So if you have, say, a 256 cross 256 cross 256 image, then you can take on chunks of, say, 100 cross 100 cross 100 and do your augmentation that way. So let me just see if I have that augmentation thing over here. Yep. Uh, so it is involved like, yeah. So yeah. So as I said, you can augment it simply by using this 3D patches. So you can augment and crop 3D patches. So data augmentation in 3D is done by using like cropping the image as well as transforming it similar to how you can crop a 2D image and transform. So the basic concept is the same, just that you're doing it for 3D images rather than 2D. And if you just go over the image processing and computer vision functions, you'll see that most of the image processing functions, or I think almost all of them, work both on 2D as well as 3D images. So you can definitely check that if you are interested. So I'll just open up the deep uh, deep learning on ramp. So if you just search for deep learning on ramp over at Google, so you can open up the page here and you can simply launch the course, and it will give you like a 2-hour course outliner as well. So right from introduction to using pre-trained networks to managing your data as well as performing transfer learning. So if you're very new to deep learning, I definitely recommend going over this course there, and then there are links to more detailed courses as well. But those are paid offerings. So, yeah.
Okay, that's what with the queries. Thank you, Praful, for the
Sure.
presentation. It was very informative presentation which focused on deep learning network, programming with our deep learning, data labeling, data augmentation, hyperparameter tuning, and transfer learning.
Yeah.
And definitely it will be beneficial for the PhD, MTech, and faculty members who are doing research in this area. So thank you very much for sharing your time and experience with us. So hope for the joining us in future also.
Sure. Yeah. Thanks, Ripti, and thanks, Professor Murugan and Professor Talukdar. I think it was a
Well,
pleasure from my end presenting as well. So, yeah. Thank you. Thanks a lot.
welcome.